In this video, I will cover Pyspark pipelines. Specifically, I will talk about what a Pyspark pipeline is, why using them can be beneficial for your machine learning project, and how to implement this type of pipeline using transformers and estimators that are available from the Pyspark API in Python. So now we can talk a little bit about what exactly is a Pyspark pipeline. So a pipeline is a software architecture that consists of executing a series of processing steps that are arranged in sequence on any given data that we have available. So each processing step in this sequence is termed a stage. Now, we can have as many steps in our application as is needed to achieve whatever goals we desire. So that could be either in terms of data cleaning, in terms of feature generation, modeling, or any type of post-processing that is required. Now, in the framework of Pyspark, these stages fall into two different possibilities. So a transformer is a Pyspark class that has a very simple API. It takes in a data frame, performs an operation on that data frame, and then returns the output also as a data frame. An estimator is a bit more complicated. An estimator takes in a data frame and then trains a model and returns a transformer. So those are the two key differences between estimators and transformers. That's how they work. Normally, when we assemble a pipeline in Pyspark, if it contains any estimators, it's required to perform a fit operation first, and then you can take your fitted pipeline and execute a transform operation on it. If your pipeline is just composed of transformers, you don't need to do this initial fitting step. You can just use your pipeline model directly. So what are some of the benefits? Why would we want to go through this exercise of designing our Pyspark applications using these pipelines? So the first point is that making use of Pyspark pipelines forces us to build an application that is composed of modular components. And these components then can be reused if designed properly. We can reuse those in other applications. It also means that the code, it's much easier to design unit tests because we've compartmentalized the logic in our application into discrete classes. It's much easier, much more intuitive to design a suite of unit tests to cover all these different components. Another point is that pipelines yield themselves to enhance automation. So this type of architecture is also ideal for organizing production quality code for extraction, transform, and load operations. So the expectation here is that the system will operate independently over some period of time, and we need a very well-designed sequence of logic in order to carry out these operations. Pipelines also facilitate scalability naturally. You can remove stages from your pipeline, but you can also add stages to your pipeline pretty seamlessly. So it's very easy to design an application that has this kind of flexibility by simply organizing our code base around the use of transformers, estimators, and pipelines. In addition, and the final point is that native to the logic within Pyspark pipelines, we also have the ability to save an entire pipeline to disk. So after if we have an estimator present in our pipeline, if we need to save a trained model, but also in addition to it, save the pre-processing and post-processing steps that are present, all contained within one object, we can do that very easily by making use of Pyspark pipelines, and then load that trained model later for use. So it's much easier to manage different models that we have running. So in the next part of this video, we'll now jump into a Jupyter notebook and work through a very simple example of putting together a Pyspark pipeline. So now we're in a Jupyter notebook. I will assume that you have a Python virtual environment already installed on your machine if you want to work along. Note that this notebook is available on my GitHub, and in the description below, I will attach a link to this notebook. So you can feel free to pause the video, download this notebook and follow along, or you can watch the video first and work with the notebook later. It's up to you. So the first thing we're going to do here is install all the packages that we will need and set up our Spark session. So let's just execute these cells. Okay, and now I'm going to load in the data set. Here, I'm going to be making use of the California housing data set that's available from scikit-learn. So we can bring that in and take a quick look at the input features that we have to work with. So here we see a few features. Now, if we want to get a better sense of these data, we can generate a box plot. And this shows all the predictive features that we've got, and it's pretty obvious by just looking at this box plot that different features are on different scales. So that's something that we will have to treat for later. We can also produce a histogram of our label, and note that the label in this case is the median house value. So let's generate that histogram. And here we see the distribution of house values. Now, note that for the purpose of this example, I'm not going to do anything to try and treat for the housing labels. They do look highly non-normal. And in this case, for this modeling example, I'm going to try and use a linear regression, which normally we would want our labels to be normally distributed. But just for the case of simplicity, I am going to ignore that. So the next thing that we can do here is produce a train test split using the Pyspark random split function. So here I've already converted the data frame from pandas into Pyspark, and now I'm going to be allocating 80% of our data for training and the remaining 20% for test. So let's execute this. So now the first thing that we have to do is assemble our input features. The way that estimators or models work in Pyspark is that all the predictive input features have to be present in a single column. So each column or each entry in this column will be an array of all the values across all the different features. So what we use to do this is something called vector assembler. That's right here. We imported that above. And now this is a transformer that comes with Pyspark, and it accomplishes just what I mentioned. So what it's going to do is it will take all these columns that I've defined to this argument called input calls, and it's going to place them all under a single output column called features. And each entry in features is just going to be an array of the original values. So calls itself is just going to be here. This is how I set it. It's just all the columns that are present in the training data minus the last one, which is our label. So we can declare an instance of vector assembler, and then because it's a transformer, if you remember what I mentioned earlier, the way that a transformer works is that with the transform method, we simply input our data frame and we get back a data frame. And the output data frame in this case will just be exactly the same as the input, except it will have this additional column called features. So let's execute this cell now. And here you can see that this data frame is pretty much exactly the same as the one that we have here up above, except that we've got this additional column features that wraps around the screen a bit. Okay, now the next thing is to treat for the different scales of the data. And so we're going to use a standard scaler that, again, we also imported from Pyspark up above. And we're going to use this to standardize all the input features to have a mean of 0 and a standard deviation of 1. Now the way we're going to do this is we will first declare an instance of standard scaler, and that's what I'm doing in this line here, where I specify the input column. That's going to be features, what we defined above. And I'm going to also specify the output column, and I'm going to call that standard features. Now, because standard scaler is an estimator, we first have to execute this fit operation. Now, what fit is going to do is it takes in our input data and it returns a transformer. And the transformer here is called model. Now, so what happens here is that scaler trains itself. It basically trains an instance of the standard scaler model or the transformer version of standard scaler in order to perform the operations that we want. And so now with model, since it's transformer, we can now execute the final step, which is just this transform method, and it takes in the training data again and returns the same data frame, but now with an additional column again, which is going to be called standard features. So we can run this cell and now generate some plots to see what our results look like. So here we can see overall it looks like things have flattened out a little bit more compared to above, but let's zero in a little bit on the horizontal axis. And here, yeah, you can see that even though there is some deviation, we can see that the median is dancing around the 0 line a little bit, but overall, yeah, these data are pretty much normalized at this point. So now we're going to move forward with our modeling task. And as I mentioned above, we're going to be using linear regression. So this instance of linear regression, this is also something that we imported above from the Pyspark API. This is an estimator again. So we will also have to train it and then execute the transform method on the trained model. So here when we declare the instance of our linear regression model, we specify the features call. This is the set of predictor features that we want to use, and so that's just standard features. And we're also going to mention the label column so that we can train effectively. We also specify a regularization amount, and that's just from this reg param here. So we can execute this cell to train the model. And now we have a transformer, which is called model. And we can use that in the next cell to generate predictions. Now, just for the purpose of seeing whether this worked at all, I'm going to generate predictions on the training data. So these should be fairly reasonably close to what the predictions are. The true values and the predictions should be pretty consistent. And so here we have the results, and they are not so bad. that we do see some differences, and again, this is a pretty simple model, and the data preparation wasn't that extensive, but it's just meant to illustrate the point that we can execute these steps to build a very simple modeling package. And so we can see here that it works. So now that we've done all this, we can ask ourselves if there's perhaps a cleaner way to go through all these steps. And that is exactly what we're going to do now below. So instead of executing all these steps separately, we're going to package everything up together into a pipeline. So the first thing we need to do is regenerate our train test data. So I'm going to do that same as before. And now let's package up all three steps that we did. So that includes the vector assembler, the standard scaler, and the linear regression model. I'm all going to package that up into a pipeline. So this is what we imported above. And what we have to define in pipeline is this argument stages, which takes a list of all the transformers and estimators that we want to execute on input data. And these stages will be executed in series. So first we're going to take care of the vector assembler, then the standard scaler, and then finally the linear regression model. So we can run this cell, and now this creates an instance of our pipeline. Now, because this pipeline contains estimators, that's the standard scaler and the linear regression model, we first have to train the pipeline. So that's what we're going to do now in this cell. Okay, and now model in this case is still a pipeline, but it is a pipeline composed solely of transformers. And so because of that, now we can run the transform method, and we're going to run it on our test set and use it to generate predictions. So now this test set's going to run through all the data preparation that we specified and give us the end product right away. So let's do that. And now we can view how good our predictions are with the true labels. And we see it's not so bad. At least this is just for the first 5 entries in the data frame. It's pretty consistent with what we saw before. We can also compute the mean squared error, and that's what I'm going to do in the next cell. Okay, and for mean squared error, we get a value of approximately 0.5. And if we keep in mind what we saw above with the distribution of our label, so we have a mean squared error of 0.5. These are the rough values of the median house values. So this is not a bad result. It's not the best result, but it's, considering the simple nature of the application we've built here, it's not so bad. So this is great. This shows how we can package everything up into a pipeline and make use of it. The last thing I want to show you guys is how we can save a pipeline to disk and then make use of it later. So let's say that, okay, we've already built our pipeline, we've gone through training it. That's great. We are happy with that. Now we want to save it for a later use. We can do that in Pyspark by simply running this command. So we've got the trained model, and we simply run write, overwrite, save. And here in save, I specify in what the name of the folder will be when we save it. So I can run this, and now, let's say later on, I want to load back in this trained model. We can do that. Now that's in model 2. And now let's generate predictions from this model right away. Okay, and so here we see values. We can tell right away that things are working, and these values are exactly the same as what we got up above. So this demonstrates how this is working and how you can make use of Pyspark pipelines. So this concludes the video. I hope it was able to help you understand how Pyspark pipelines work and why we may want to use them. If you have any questions, feel free to leave them in the comments below. If you liked this video or the content on this channel in general, please like, share, and subscribe. It's always appreciated. And I will see you in the next video.